Hello, everybody. Today we are going to discuss chapter 5.3, 5.4, and 5.5. Okay. Uh, First of all, let me share the screen with you. Okay. So in the previous sections, we discussed confidence interval, such as large sample confidence interval for population mean and the confidence interval for proportions. In section 5.3, we discussed small sample confidence interval for population mean. Okay. Remember, in section 5.1, we require the sample size is large. Okay. So if the sample size is large, no matter what type of distribution, we can assume based on central limit theorem, the population mean follow a normal distribution. Okay. However, when the sample size is small, there's no good general method for finding confidence intervals. Okay. However, when the population is approximately normal, we can use another distribution, which is called student's t distribution, to calculate the confidence interval for a population mean. So what can we do if the sample mean is the mean of the small samples? So when the sample size is small, less than 30, the sample standard deviation may not be close to the population standard deviation sigma. And the sample mean may not be normal. Okay? But if we know nothing about the population, then there's no easy way to calculate the confidence interval. However, if we know the population is normal, then the sample mean is also normal, even the sample size is small. Okay. Then we calculate another parameters. Okay. But because the sample standard deviation is not close to the population standard deviation, the quantity has another name, which is called student's t distribution. Okay. Similar to normal distribution, student's t distribution, the density function is also very complicated. Okay. But we do not need to know about the distribution. Similarly, we can use another table which is similar to the z table. It's called t table, which is the table 8.3 in our textbook. Okay. So we use that table to find out the probability. Okay. Let's define x1, x2, xn is a small random sample. The sample size is less than 30 from a normal distribution. This is the requirement. It must have a normal distribution, so we can use student's t distribution. Okay. The population has a mean value of mu. Okay. Then the t value, which is defined here, this is sample mean minus population mean. Here is the sample standard deviation, and this is the sample size n. Okay. For students' t distribution, there's another parameter which is called degree of freedom. Okay. So degree of freedom is equal to n minus 1, which is the sample size minus 1. Okay. Remember, the n needs to be small. Okay, then we use students' t distribution. If n is large, then we do not need to use students' t distribution because in that case, we can use normal distribution as we discussed in section 5.1. Okay. The curve, a density function of the student's t distribution, is depending on the degree of freedom, which is a -1. Okay. The difference between the t curves and standard normal distribution is t curves are more spread out with higher standard deviation compared with standard normal distribution. Okay, and the table is 8.3. Table 8.3 in your textbook, and we call that the t table. Okay, here is the t table, the table 8.3 from our textbook. V is the degree of freedom. And first of all, we need to calculate the degree of freedom based on sample size n minus 1. Okay. And the alpha in the first row is the probability. And the values here is called t-value. Okay. And the t-value is equal to the sample mean minus mu over s divided by square root of sample size. Okay, so this is how we use the t-table. And here compare the student's t-curve with different degree of freedom. This is t1, which means the degree of freedom is 1. t10 means the degree of freedom is 10. As we can see, the smaller the degree of freedom, the higher the spread. Okay, the higher the degree of freedom, the smaller the spread. And here shows the z-table, the pink solid line, the z curve, which is normal curve, so it has less spread compared to student's t curve. Okay. Okay, so then let's do a question together. A random sample size 10 is to be drawn from a normal distribution with a mean sample of 4. If student's t statistics t-value is calculated as this. Okay, the question is asking what is the probability of t larger than 1.833. Okay, so what we do is we calculate the degree of freedom, which is n minus 1. So 10 minus 1 is equal to 9 degree of freedom. Okay, then let's go to the t-table. Okay, for t-table, degree of freedom of 9. Okay, asking what is the probability t-value larger than 1.833. So 1.833 is here. Okay, and the corresponding probability is 0.05. Okay, so larger than 1.833, the probability, which is the shaded area here, is 0.05. Okay, so I guess as we see from here. Another example asking what is the value for T14 distribution whose lower tile probability is 0.01. Okay, so we know the t-curve is symmetrical to its center line. Okay, as we can also see from here, the table 8.3 shows us, sorry. Sorry, where is it? Okay. So table 8.3 shows us the right-hand tail, okay, but because it is symmetrical to the center line, the question is asking for lower tile probability, okay, of 0.01. So what we're going to do is we first look down the column headed with 0.01. Okay, 0.01 is here. Okay. And also for degree of freedom of 14, the 14 is here. Okay, so from there, we have the t value of 2.624 for 0.01 probability and degree of freedom of 14. So that is 2.624. Right. So that means the t value here is 2.624. But because, again, the curve is symmetrical to 0, 0, the lower hand corresponding to 1%, 0.01, should be minus 2.624. Okay, so that is the answer. Okay, so the answer is minus 2.624. So in general, if we define x1, x2 to xn is small random sample from normal population. So again, this is a two requirement for us to use students t distribution. Small sample, normal distribution. Okay, remember that. Okay, and then for any confidence interval, we can use this equation to calculate that. Okay, this is t with degree of freedom n minus 1 for half alpha. So again, we must have a sample come from population that approximately normal. Okay, and these samples should not have outliers. Okay, and here shows a special situation. Sometimes a small sample may be taken from a normal population, and if we know sigma, the population standard deviation, then we do not need to use students t distribution because we know the sigma. So remember, if we know the population standard deviation sigma, we should use the z table, not the t table. Okay, so this is a special case. So use z table, which is table 8.2. Example 8, engineer read a report that a sample of 11 concrete beams, okay, this is small sample, have average compressive strength of 38.45 megapascal with the standard deviation 0.14. Okay. Should the T-curve be used to find the confidence interval for the mean compressive strength? Okay, we know this is small sample. Sample size is 11 is small sample. Remember, another requirement for that is the sample need to follow a normal distribution. Okay, look at the question. The question does not tell us the sample follow a normal distribution or not. So we do not know that, so we cannot use student's t distribution to calculate the confidence interval. So the answer is no. Okay, because we do not know it follow a normal distribution or not. Here is another example. The article, direct strut and tie model for pre-stressed deep beams present measurement of normal shear strength for a sample of 15 pre-stressed concrete beams. So 15 is small sample, and here shows the result. Assume that on the basis of a very large number of previous measurement of other beams, the population is known to be approximately normal. Okay, so they follow a normal distribution with a standard deviation sigma of 180. In this case, we know the population standard deviation, which is 180. The question is asking 99% confidence interval for the mean shear stress. Okay, so we know you follow a normal distribution, and also we know it is a small sample. Okay, so normally we should follow student's t distribution. However, the sigma is there. Okay, we know the sigma. In that case, we do not need to use student's t distribution. So instead, we use normal distribution. Okay, so from 99% confidence interval, so half alpha is equal to 1 minus 99 divided by 2. So half alpha is 0.05. Okay, and from the table 8.2, so table 8.2, the z table, the half alpha is 2.58. Okay, so 99% confidence interval in this case will be the mean value plus minus z half alpha okay, and the sample mean we can calculate based on the values from the question. Okay, we calculate the sample mean. Z half alpha is 2.58. Sample standard deviation. Sorry. Okay, here. Sample standard deviation. 180 divided by sample size, square root of sample size 50. Okay, all right. So that is section 5.3. Section 5.4 is confidence interval for the difference between two means. Okay, so let's look at a setup. If x and y are independent and both x and y follow normal distribution, okay, And then based on the linear function of normal distribution, we know x plus y follow a new normal distribution. And also x minus y follow a normal distribution too. Okay, pay attention to standard deviation. The variance is both plus. Okay. If x1, x2 to xn, a large random sample from population mean of mu x and the standard deviation of sigma x, and if y1, y2 to yn, this should be ... sorry, okay, is another large sample of sample ny from a population with a mean value of mu y and the standard deviation of sigma y. Okay. Then, if the two samples are independent, then we can calculate the confidence interval of mu x minus mu y based on this equation. Okay, this is z half r. This is sample mean of x, sample mean of y, standard deviation, and the sample size for x and y. Okay. If we do not know the population standard deviation, we can use the sample standard deviation Sx and xy instead. Let's look at an example. The chemical composition of soil varies in depth with depth. Article in a certain journal describe chemical analysis of soil taken from farm in Western Australia. Okay, so 50 specimen. So from there we know this is a large sample because this is more than 30. Okay, were taken at depths of 50 and 250 centimeter. So at two depths. Okay, so at each the depths we have 50 specimen. At depths of 50 centimeter, the average NO3 concentration was 88.5 and a standard deviation of 49.4. At the other depths, the average is this and standard deviation of 51.5, asking for 95% confidence interval for the difference of NO3 concentration. Okay, first of all, we need to find out which set of equation to use. This is confidence interval for the difference between the two means. Okay, so so if we define x1 to x50, a concentration of the 50 specimen at 50 centimeter. Okay, so then the mean x tells us is 88.5. Okay, and the sample standard deviation is 49.4. Okay, for the other depths, defined as y1 to y50. Okay, this is 250 centimeter depths. The mean value y is 110.6 with sample standard deviation sy 51.5. Okay, so and because n is equal to 50, so this is a large sample. Okay, so the difference in the mean value mu y minus mu x based on the equation from the previous slides is equal to sample mean of y minus sample mean of x plus minus, this is 95% confidence interval. This is z table. The z half alpha will be 1.96. Okay. And based on the equation, this is sx squared, so 49.4 squared divided by the sample size 50 plus sy squared, so 51.5 squared over 50. Okay. So the answer is 22.1. Sorry. Okay. Right. So that is section 5.4. And last section we're going to discuss today is section 5.5, which is confidence interval for the difference between two proportions. Okay, so this is similar to section 5.2, which is confidence interval for proportion. Okay, but here is difference between two proportions. But you will see the equation are pretty much similar. Okay, so let's look at the setup. If X is the number of success in NX independent Bernoulli trial, and success probability is Px, okay, and Y is number of success in NY independent Bernoulli trial with success probability of Py, okay, and we know X will follow binomial NX Px, and Y will follow binomial NY Py. Okay, and this is the modified N and modified P. Okay, this is pretty much the same as we discussed in section 5.2. Just make the result more accurate. Okay, and the confidence interval for the difference between the two proportions shows here. Okay, so for any level of confidence interval, the difference between Px minus Py is this. Okay, so again, this is modified Px as we showed in the previous slides, modified Py. This is z half alpha from the table 8.2. Okay, this is modified N. Okay, the lower limit of this confidence interval should be -1 because the lowest case will be 0 minus 1 equal to -1. So cannot be less than that. Upper limit for the confidence interval is 1 because the highest possible value is 1 minus 0. Remember, this is proportion. Proportion should be large or equal to 0 and less or equal to 1. Okay, so from 0 to 1. Okay, so the upper limit is equal to 1. So if we calculate the value larger than 1, we need to replace it with 1. Okay. And here says there's a traditional confidence interval method, but we're going to use this equation, which is more accurate. All right, so here is an example. Okay. Method for estimating strength of stiffness requirement should be conservative that this should overestimate rather than underestimate. The success rate of such a method can be measured by a probability of overestimate. An article in a certain journal represent the result of an experiment that evaluate a standard method for different estimating the brace force for compression web brace. Okay, so in a sample of 380 short test column, the method overestimate the force for 304 of them. And in a sample of 394 long test column, the method overestimate the force for 360 of them. Okay, the question is asking for 95 confidence interval for the difference between the success rate for long columns and short columns. Okay, so this is confidence interval for the difference between two proportion. This is success rate, which is a proportion. Okay. So let's do this together. First of all, we calculate the modified x. Okay, the modified nx based on the equation is nx plus 2. Okay, and this is modified px. So based on this equation, so nx is equal to 380 plus 2. Okay, and modified px is equal to 304 plus 1 divided by 82, sorry. Okay. And modified y is equal to 394 plus 2. Okay, so py is equal to 360 plus 1 divided by 396. Okay. And then the question is asking for 95% confidence interval. So z half alpha is equal to 1.96. Okay. So based on the equation, px minus py. Okay, this is what the question asks. The difference between the two proportions. So px plus minus py plus minus z half alpha. Okay, it is modify px 1 minus modify px. Okay, this is modified nx. This is modified py 1 minus modified py divided by modified ny. Okay, and we know for px it is this. .7984. This is py is 0.1996. Okay, so let's define okay. This should be y, py, because py is higher, sorry. Px is smaller. So that will equal to 0.9116 minus 0.7984 plus minus, so z half alpha is 1.96. Okay, and then we just plug in the values of modified px, okay, which is 2.7984, modified nx, which is 382, modified py is 0.9116, modified ny is 396. Okay, ignore the details. The answer will be okay. All right, so that's the sample example for difference between two proportions. Okay, so that's the end for this class.